In this video, some examples are discussed that demonstrate our current inability to deal with continuity, infinity, and what a number is. The first example is about a formula that Leonhard Euler constructed centuries ago. Its meaning is still unclear to current mathematics. The formula sort of makes fun of the use of dot dot dot. Dot 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 indicates the progression to infinity. Here it is. Dot 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 plus x to the third plus x squared plus x plus 1 plus 1 over x plus 1 over x squared plus 1 over x cubed plus dot 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 is equal to 0 for all x not equal to -1, 0 or 1. For proof, multiply the left side f of the formula by x squared, while thanks to the dots x squared times f is f, which is equal to x squared minus 1 times f is 0, and if x is not equal to -1, 0 or 1, then f must be 0, quod erat demonstrandum. The only reason for the existence of this proof is the two series of dots, suggesting infinities. The formula without the dots is not true. The meaning of Euler's formula is unclear in current mathematics. It is totally clear when you accept that infinities do not exist. The dot 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 construction is an ill-defined construction. It's a nonsense construction. The formula has no further meaning. You can do the proof by multiplying both sides of the equation by x to any power except for the power of 0. That should give you a clue already. I would like to think Euler instinctively knew this. Here is another example. According to current mathematics, there are infinitely many prime numbers. The proof assumes that a new prime number can always be constructed from all known ones. However, this proof only proves that there is possibly an ongoing growth in the number of prime numbers that one can know. This is assuming that the construction process is manageable. It does not prove anything about the ill-defined infinity of existing prime numbers. Does a prime number exist if it cannot be written down or known? Is being not a requirement of existence? We cannot construct the next biggest prime in the realm of big numbers, or more accurately, of big symbols. Big numbers or big symbols do not exist, as we have seen in the video on distinction. So, big primes don't exist either. We cannot identify big primes. The difference between big primes cannot be established, and multiplication cannot be done anymore, not in time, not in space. Never-ending processes are also supposed to be involved. In other words, the new biggest prime cannot be found or written down. All we can say is that we will not know exactly how many primes there are, because we will enter the realm of big symbols at some point, but we cannot know where that realm starts. Another example. Neither the rationals, the reals, nor any other number system produces a continuum. Cantor's diagonal argument to prove that the reals are of higher cardinality than the rationals is a vacuous proof, using an illegitimate argument. We should already have argued the following. You cannot always find a number outside some known growing list of rationals using an ongoing process. You cannot enter the realm of big symbols. Furthermore, it would only prove that it is an ongoing list to which that number, if found, can probably be added, not an infinite list. It is incorrect to claim that the ongoing list of rational numbers is infinitely long and a complete list of rationals, and that therefore the new number cannot be rational because it's not on the list. Because the proof is not correct, there is no reason to assume other types of infinities. The cause of Cantor's flawed argument is the absence of proper definitions for infinity and number. The continuum hypothesis is now also decided. A last example. The fundamental theorem of algebra can be saved by adding the in-between in mathematics. The theorem does not have a justifiable proof yet. The theorem states that every non-constant single variable polynomial with complex coefficients has at least one complex root. Suppose we do not accept some irrational complex solution for the simple fact that they do not represent identifiable distinguished numbers. They do not meet the requirements to be called a number. In that case, any random polynomial, for example the simple y is x to the fifth minus 2x plus 3, will almost certainly have no roots. The roots will lie somewhere on an in-between. If we do not accept in-betweens, we should not accept the fundamental theorem of algebra. We need to adopt in-betweens in order for the intention of the theorem to be saved. Without the in-between, we have to change the theorem into a theorem of approximate complex roots, if numbers are required as roots. I'm sure you can find your own examples.